talking about states of matter: liquid, gas, and solid. What does it get to convert them together? What is the behavior if we take a substance in one of these three states and heat it or cool it? How are we going to observe the states? How would the temperature of these systems behave? So we are studying those under heating and cooling curves. In order to discuss this, I'm going to define two things for you. Two terms. Heat of fusion. Guys, if you want to melt ice, do you need to heat ice to melt?
Yes.
Think of getting 1 gram of ice, tiny amount. The amount of heat needed to melt 1 gram of ice at 0 degrees of Celsius is called heat of fusion. So fusion, melting. Heat of melting. How much heat do you need to melt the solid? How much heat do you need to melt 1 gram of a solid at its melting point? That's called heat of fusion. And guys, if you have 1 gram of water, you want to evaporate 1 gram of water, do you need to apply heat? So we call that heat of vaporization. Amount of the heat needed to evaporate 1 gram of water or 1 gram of any liquid at its boiling point is called heat of vaporization. Are you with me so far? Any questions so far? All right, if I go to the next slide. Well, suppose you are taking some ice, and this ice is coming from your freezer. Usually, coolest temperature you can get on a freezer is -20. Typical home freezer. If you get some ice from your freezer, if you're adding heat to this, the temperature of the ice is going to rise, let's say from -20 to -10, and then eventually gets to 0 degrees of Celsius, which is melting point of ice. When you get to the melting point of ice, you see the solid is melting. You are adding heat, but the temperature is not rising. See, temperature stays the same. You're adding heat. Temperature is not changing. So where is the heat going? The heat is being used to break the bonds between solid molecules, to break the bond, to break the forces between two molecules, intermolecular forces. And this temperature remains fixed unless the last piece of ice is melted. You have one phase, you have only water. Then as you apply heat, temperature is going to rise, let's say to 10, and then 20, and then 50, and going higher and higher until it gets to 100 degrees of Celsius. So what is happening here? We are heating, temperature remains fixed. Why is temperature being fixed? Why we are applying temperature heat? Why temperature is not rising? Because liquid is evaporating, because it's heat of vaporization. It's the heat needed to break interaction between liquid molecules. So molecules can become free and fly away as gas. Temperature remains constant until the last drop of liquid is evaporated. When you have a single phase, you have gas, temperature is going to rise. So what I would like to bring to your attention is the fact that whenever you have mixture of two phases, temperature remains flat, although you are applying heat. Why temperature is remaining fixed between these 2 points while I'm applying heat. So heat is being used as heat of fusion. Heat is being used to break the interaction between solid molecules. Heat is being used to cause melting. And at this flat area, we are applying heat. Temperature is not changing. Why? Because heat is being used to break interaction between liquid molecules. So this is heat of vaporization. I don't know if you have noticed, guys, sometimes you are baking potatoes in boiling water, and water is boiling, and you may increase the heat for the temperature to go up, but during boiling, temperature remains the same. You apply heat, the water is going to evaporate. Its temperature, the temperature of boiling water remains the same. Doesn't matter how much heat you apply. The temperature of melting ice remains the same. Doesn't matter how much heat you apply to ice. Until ice is converted to water, temperature doesn't change. So what is the heat being used? To break the interaction between solid molecules. If I go to next slide, go ahead, guys. Would you try to answer these questions? See if they make sense to you, please. Good job, Victoria. Good job. Are you ready, guys? Do these make sense? Any question? All right, if I go to the next slide, you see the same behavior when you're cooling the system. Suppose we start with hot steam at 140 degrees of Celsius, and we are placing this, let's say, in ice or a cold surface. We are removing heat. What's going to happen to steam if you are cooling it off? It's going to lose temperature, going from 140 to 120 to 100, and 100 is the boiling point of water. That means when a steam reaches 100 degrees of Celsius at 1 atmosphere pressure, start condensation, it becomes water. So now you have a mixture of water and steam. We are removing heat. How come temperature is not dropping? How come temperature is flat? Because when the steam is converted to water, there is interaction between molecules. Remember, liquid molecules attract each other. That attraction is releasing heat. So we are removing heat, and heat is being released by conversion of steam, by condensation of steam to water. That's why temperature remains flat. Again, we have a mixture of two phases. You have a plateau of temperature. As soon as the last amount of steam is condensed to water, now you have pure water, you are removing it, temperature is going to drop rapidly. It goes from 100 to 90 to 80 to 60, 40, 20 at 0 degrees Celsius, which is the melting point of ice or freezing point of water. You know, freezing point and melting point are same temperature. The directions are opposite, but they are the same temperature. So when we get at 0 degree of Celsius, now water is becoming ice, is solidifying during conversion, freezing of water to ice. We have two phases, temperature remains the same, remains a plateau. Until the last drop of water is frozen, then you are removing it, the temperature is going to go down. So we see the same observation, whether it is cooling curve or heating curve. Whenever you have a mixture of two phases, temperature remains a plateau.
So is that flat line like the kind of the equilibrium state when there's a mixture? And so as you're removing heat, it's not there, you're still going to have water and steam, but as you're removing heat, you're having more water than steam, but it's like staying in that same kind of range.
Excellent, Victoria. That is the brain of a mechanical engineer. I love that. Yes. Good job. When we have a mixture of two phases, there is equilibrium. We're pushing equilibrium to one side by removing heat or applying heat. Once we reach to one phase, now equilibrium is gone. There are no two phases. So the one phase is responding to change of temperature. Yes. Good question. Thank you. Good job.
Well, if I'm freezing water, there's a certain point to which once it's frozen, I can't make it any colder because it's already frozen, just like the heat, right? Or is that incorrect?
That's incorrect. That's incorrect. See, you can have ice which is minus 20.
Because like dry ice and everything, right?
No, dry ice is carbon dioxide, even water, ice, H2O. Once you freeze it, it's one phase. It's only solid. You remove heat, the temperature is going to drop.
So in the process of going from water to ice, at that stage, well, I'm just thinking because there's a plateau, I'm noticing that the temperature isn't dropping.
Yes, going to ice from water, yes, remains a plateau.
Huh. So during that plateau phase, it can't get colder because of that transformation.
Because heat is produced. What is the heat which is produced? Water.
Water
is becoming ice. That means molecules are producing attractive forces. Intermolecular forces is being made. It's bond formation. Bond formation is releasing it. You're removing heat, but heat is being released by conversion of water to ice. Why? Ice has less energy. Water has more energy. So energy is released when we go from water to ice.
That's crazy.
And we are removing heat, so these two are balancing each other.
So when potatoes are boiling, that's why you're saying it can't get any hotter because it's in that stage of water transforming into gas.
Correct. Yes.
Okay.
Good job. Yes, it's right in here.
Thank you.
100 degrees of Celsius. Good question.
Gotcha.
I like the way you ask questions, deduct, and come to conclusion. That's very good. That analysis is required for critical thinking. Good job. And who is this, Brian?
No, it's Caleb.
Good job, Caleb.
Thank you.
Keep doing that. Guys, you don't have to be doing chemistry to do that. Continuously in life, ask yourself question from what you observe, analyze and come to a conclusion. That's how you increase the ability of problem solving, critical thinking, and analytical skill. Good job, Caleb. Go, guys, see if you can answer these questions. Good job, Victoria. Yeah, keep going, guys. You're doing very well. I'm impressed. Good progress. Any questions, guys? Do this make sense to you?